Hi, and welcome to the Section 3.3 video lecture for Calculus 1. Go ahead and take out your note sheets, the handouts, which can be found either on my math lab under handouts or in the Blackboard course in this week's link, depending on which class format you're in. So what we're going to talk about today in section 3.3 are differentiation rules. So far with differentiation, the only way we've known how to find derivatives is through the use of limits of the difference quotient. And that can be time consuming and cumbersome to do. So one of the things that has happened over the last couple hundred years since the development of calculus is that people have spent a lot of time coming up with simpler ways to do derivatives and proving those to be true. So we're going to look at those rules today, and it's going to make it a lot less complicated to calculate most derivatives. And then what we're also going to look at is we'll do some of those proofs, not all of them. I've got space in the notes to do all of them, but for time purposes, we'll focus more on how to use this and less on how to prove these rules. So if y equals f of x is a differentiable function, then its derivative is f prime of x is also a function. If f prime is also differentiable, then we can differentiate f prime to get a new function of x denoted f double prime. So f prime prime equals f prime prime. The function f double prime is called the second derivative of f because it is the derivative of the first derivative. It is written in several ways. They're all listed here. The most common being these first two simplified forms, and then this is actually a nice way to write that you want to take the derivative of the first derivative, which then can be simplified down to this. And if you look at this one right here, what you'll notice is if you multiply these together, on top you've got d times d is d squared, and on the bottom you've got dx and dx, which is dx squared. So that's where this second derivative notation. And then there's a few other ways to write it, which include y double prime and so on. So if y double prime is differentiable, its derivative, y triple prime, is the third derivative. And beyond the third derivative, we stop using these dash marks and instead put parentheses around an exponent with the number of derivatives. So y to this nth power thing here, or d sub n over n of the x, is simply the nth derivative. So anything beyond 3, we use this notation. Okay. Now, let's start getting, so that's some just notation on doing multiple derivatives. Now let's start getting into some of the rules. So the first rule is the constant function. So if f is a constant value, f of x equals c, then the derivative of c is 0. So we could try doing that derivative real quick here. So if our function is f of x equals c, some constant number, then f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? And now f of x plus h, f of any value, when you have a constant function, is c. So this would be c minus c over h, the limit of that, as h approaches 0. c minus c is 0, so that's the limit as h approaches 0 of 0 over h, which is the limit as h approaches 0 of 0, which is just 0. And so we can see that if we take the derivative of a constant function, we always just get 0 out. Okay, here's one I'm not going to do. Show you the proof of, but this is a really important rule, the power rule. So the power rule says that the derivative of a variable to the nth power is equal to n times the variable to the n minus 1 power. So to give you an example of this, or a few examples, if we took, instead of doing the proof here, let's just do some examples. So if f is, let's just do the first few. Sorry, I skipped one. Okay, and we can look at these. Then f prime, the derivative, is simply you take n, which in this first case is 1, times x to the 1 minus 1 power, which gives us x to the 0 power, which is 1. Okay, so if you have x without an exponent, you just get 1. So then we can go on from there. So for the second one, this would be 2 times x. The next one would be 3x squared, and then 4x cubed. So you bring the exponent out in front, and you subtract 1 from the exponent to give you the new derivative. Okay, so there's another example. Another really important proof is that if you have the derivative of a constant times a function, the constant does not change. So to give you an example, let's use one of the ones up here. If my function f of x was 3x to the fourth, and I want to do the derivative of that, so f prime of x is the derivative of 3x to the fourth, that's going to be 3 times the derivative of x to the fourth, and then that would be 3 times 4x to the third, which is 12x to the third. So if you have a constant multiplied by a function, you can just multiply the end result of the derivative of the function by that constant. So the 3 we just ignored here to do this derivative, do the derivative of x to the fourth, and then multiply 3 times that derivative. And that gives us the answer down here. Another really important rule is that the derivative of a sum is those two derivatives separately. So that's what this one says. So what all these rules we've looked at so far is it makes it really easy to deal with derivatives that involve polynomials especially. So if I look at this problem here, if I want to find the derivative with respect to z of 3z to the 7th minus 7z to the 3rd plus 21z squared, to do that, all I'm going to worry about are these. What are these derivatives? And the rest of these operations are going to stay the same because by using the constant multiple rule and the sum and difference rule, I can rewrite this as the derivative of w with respect to z of 3 times the derivative with respect to z of z to the 7th minus 7 times the derivative of z to the 3rd plus 21 times the derivative of z to the 2nd. Okay, and so by using the constant multiple rule and the sum rule, we're really just finding the derivative of these three things I underlined and then multiply them. So this would be dw over dz would be 3 times 7z to the 6th, right? I bring the 7 on front and subtract 1 from 7 with a 6, minus 7 times 3z squared plus 21 times 2z, right? So the constants, coefficients there, I just bring along. Okay, and so that's going to give us dw over dz. The first derivative of this with respect to z is 21z to the 6th minus 21z squared plus 42z. And that's the first derivative. And so then if we want to do the second derivative, we would do the same idea. So I would take the derivative with respect to z on both sides, right, because it's asking us to find the first and second derivative. Okay, and so now we can do exactly what we did with writing out less steps. I'm just going to worry about the derivatives of these three pieces, the z to a power. So this would be d squared w over dz squared. The second derivative of w with respect to z would be 21 times the derivative of z to the 6th, which is 6z to the 5th, minus 21 times the derivative of z squared, which is 20, which is 2z, and then times 42 times the derivative of z, which is 1. So the second derivative of w with respect to z is 126z to the 5th minus 42z plus 42. Okay, and so that's the idea. So here's the second derivative, and here was the first derivative. Okay, and so once you get the hang of this, you can find derivatives really easily for things that look like this. Right? So we can apply the same rules for the second one. And I can use slightly different notation if I want, right? If I have y, I can write y prime, and now I just find the derivative of each of these terms. Now, we get to use a rule here that we haven't used yet, which is the constant. derivative of a constant. So what's the derivative of 4? Well, that's 0 because it's a constant. The derivative of 2x would be negative 2 times the derivative of x, which is x, minus the derivative of x to the negative third, which would be negative 3x, and then we need to subtract 1 from negative 3, which is negative 4. And so this would be y prime equals negative 2 plus 3x to the negative fourth. And then we could do the second derivative doing the same idea, right? Find the derivative of each term by ignoring the constant unless it doesn't have a variable. So y double prime, the derivative of a constant negative 2 is 0, plus 3 times the derivative of x to the negative fourth, which is negative 4 times x to the negative fifth. So y double prime equals negative 12x to the negative fifth. Okay, and so that's the idea. Now, with this last one, notice here that we don't have a number times a variable of power. We're dividing by the variable. So one of the things we can do here is we can rewrite this using negative exponents. So this would be 12 theta to the negative first minus 4 theta to the negative third plus theta to the negative fourth. And now we can use the same rules we used above to find the derivative of that. So this would be r equals r equals 12 times negative 1 theta to the negative second minus 4 times negative 3 theta to the negative fourth plus negative 4 times theta to the negative fifth. And then multiply that out. So r prime is negative 12 theta to the negative second plus 12 theta to the negative fourth minus 4 theta to the negative fifth. Okay, and then we could do the second derivative. So that's the first derivative, right? So, and then we can do the second derivative the same way. So r double prime would be negative 12 times negative 2 theta to the negative third plus 12 times theta to the, I missed a term there, 12 times negative 4 theta to the negative fifth minus 4 times negative 5 theta to the negative sixth. And so if we come up here, we get r double prime is 24 theta to the negative third minus 48 theta to the negative fifth plus 20 theta to the negative sixth. Okay, so that's one way to deal with this. These variables in the denominators. You can rewrite each one using negative exponents and then use these rules. There's also a way to get a rule for how this works. So if I look at, I'm going to use this first example here to make this point. So this answer for r theta, if I were to rewrite these with positive exponents, would be negative 12 over theta to the second plus 12 over theta to the fourth minus 4 over theta to the fifth, right? If we rewrote that with positive exponents, that is what r prime would look like. So what we want to do is we want to compare that to where we started. So how do we get from r to r prime? What appears to be happening to these problems? So first of all, if we look at the exponents of the ones in the denominator, we start with 1, 3, and 4, and we go to 2, 4, and 5. So that means we added 1 to the exponent. We should also notice that what did we do? Well, we multiplied by the opposite of the exponent that was there before, right? The opposite of 1 is negative 1. Negative 1 times 12 is negative 12. Here, we multiplied by the opposite of 3. So 3 times negative 3 times negative 4 is positive 12. And here we multiplied by negative 4, the opposite of this 4, because negative 4 times 1 is negative 4. So we could write a rule for how this works. So if f of x is 1 over x to the nth, well, what happened? So what is f prime of x? Well, it's you add 1 to the exponent and you multiply by the opposite of the exponent. So this would be, that was there before. So this would be negative n times 1 over x to the n plus 1. So we could use this rule to find the second derivative that we're dealing with here, right? So we could take this first derivative that we already found, and we could find its second derivative using this rule. So we multiply by the opposite of n, so that would be negative 2 times negative 12 over, and we add 1 to the exponent, so x theta to the third. Second one, we multiply by the opposite of this, so that's a positive 4, so we multiply by negative 4 times 12 over theta to the fifth. And same thing goes here. We multiply by the opposite, so negative 5 times 4 over theta to the sixth. And if I multiply those out, I get 24 over theta to the third minus 48 over theta to the fifth plus 20 over theta to the sixth. And notice that that is the same as the answer we got right here, just writing it using positive exponents, right? Because if I write theta to the negative third as theta to the third, I have to put in the denominator. Same goes for theta to the negative fifth and theta to the negative sixth. So when you're dealing with variables in the denominator, like these, you have two options. Rewrite them using negative exponents and then use these power rules, or use this altered power rule for powers in the denominator. So you don't have to rewrite it. Okay. So at this point, what I'd like you to do is flip to this next page, pause the video for a second, and try doing these three problems here. So find the first and second derivative for these three. Okay, so now that you've had a chance to try them, let's just run through them together. Okay, so for this first one, y prime, the derivative of x squared is 2x. The derivative of x is 1, and the derivative of 8 is 0. So y prime is 2x plus 1. The second one, and then for y double prime, derivative of 2x is 2, derivative of 1 is 0, so y double prime is 0. Okay, same one here. So this would be y equals 1/3 times the derivative of x cubed, which is 3x squared, plus 1/2 times the derivative of x squared, which is 2x, plus 1/4 times the derivative of x, which is 1. So y prime would be x squared plus x plus 1/4. And then the second derivative of x squared is 2x, the derivative of x is 1, and the derivative of 1/4 is 0. So y double prime is 2x plus 1. And then the last one gets even a little trickier, and we're set up in two parts, so I could do each one of these, the two different methods we've talked about. So for the negative exponent one, I'll just use the power rule. So s prime would be negative 2 times negative 1 times t to the negative second. And for this one, I can use the alternate rule. So this would be plus negative 2 times 4 over t to the third. So s prime is 2t to the negative second minus 8 over t to the third. And then we can do the second derivative. So the second derivative would be 2 times negative 2t to the negative third minus negative 3 times 8 over t to the fourth. So s double prime is negative 4 t to the negative third plus 24 over t to the fourth. Okay, so that's the idea of how we do derivatives that involve polynomials. Well, what if we wanted to multiply and divide more complicated polynomials? So that's what we're going to look at starting on the next page. Okay, now that we've talked about adding, subtracting functions, let's talk about what happens if you want to multiply them. So if you wanted to find the derivative of two functions that are multiplied together like u and v here, you're going to use the product rule. And so what that's going to be is you're going to take the function for one times the derivative of the other plus the derivative of the first one times the second function. So we can use this to deal with things that look like this. Now you could also multiply this out and then just use our normal rules, but what we want to do is practice doing it both ways here and kind of show you that this works. Okay, so what we have here is we have two different functions being multiplied together. So we've got u and we've got v. So to find y prime, what we're going to do is we're going to take u times the derivative of v plus the derivative of u times v. Okay, so u is just 2x plus 3. And then we're going to take the derivative of v. So the derivative, which we can write like this, d dx of 5x squared minus 4x. And then we're going to add to that the derivative of u, so d dx of 2x plus 3 times v, 5x squared minus 4x. Okay, and we're just going to go and multiply those out. So this will be y prime equals 2x plus 3 times the derivative here. So the derivative of 5x squared is 10x minus 4, right? The derivative of 4x is just 4. Plus the derivative of 2x plus 3, well, the derivative of 2x is just 2, and the derivative of 3 is 0, so that'll just be 2 times 5x squared minus 4x. And then we'll multiply those out. So this will be 20x squared plus 22x minus 12 plus 10x squared minus 8x. Combine like terms, and you get 30x squared plus 14x minus 12. Okay, so that's how you could do that with the product rule. Now, alternatively, and possibly a better way to do this problem would be to multiply this out. So we start with y equals 2x plus 3 times 5x squared minus 4x. We could just multiply these together. And if we do that, we get y equals 10x cubed minus 8x squared minus 15x squared minus 12x, which is 10x cubed minus, one of these should have been plus. That should have been plus 15x squared. So plus 7x squared minus 12x. And now we can just use our polynomial derivative rules that we've been practicing so far to find this derivative. So 10x cubed is 30x squared. 7x squared, the derivative of that is 14x, and the derivative of negative 12x is negative 12. Okay, so just because you can use a rule doesn't mean you necessarily should. Sometimes it's better to find alternative ways to deal with a problem. Okay, so that was the product rule. So now let's go ahead and look at the quotient rule, which is similar. So if we're dividing two functions, we take the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function over the bottom function squared. And once again, sometimes you might want to make this a little easier on yourself and go ahead and multiply some stuff out. So like here, it will probably behoove us to rewrite this as x squared plus 3x plus 2 over x squared minus 3x plus 2 when we do this derivative. So y prime is going to be the bottom function, so x squared minus 3x plus 2 times the derivative of the top function, x squared plus 3x plus 2, minus the top function, so x squared plus 3x plus 2, times the derivative of the bottom function, so x squared minus 3x plus 2, all over the bottom function squared, so x squared minus 3x plus 2 squared. Okay, and then we just simplify. So we find the derivative. We find these derivatives, so x squared minus 3x plus 2 times the derivative. Well, the derivative of x squared is 2x, the derivative of 3x is 3, and the derivative of 0 is 2. So that's 2x plus 3 minus x squared plus 3x plus 2 times 2x minus 3 all over x squared minus 3x plus 2 squared, and then we would multiply those out. So y prime is 2x cubed minus 3x squared. So I'm doing some of this multiplication in my head. If you need to write it out, that's great, but you can do that off to the side. Minus 5x plus 6, And then from that, we're going to subtract these two multiplied together. So 2x cubed plus 3x squared minus 5x minus 6 all over x squared minus 3x plus 2 squared. And now we can combine like terms. So 2x cubed minus 2x cubed cancel. Negative 3x squared minus 3x squared is negative 6x squared. Negative 5x minus negative 5x cancels. And 6 minus negative 6 is 12. Okay, and so there is our final answer for doing that derivative. So most of the time, you're going to need to use the quotient rule in these settings. Okay, so let's try another one. So another one here we could do with the quotient rule. We're dividing, so we want to rewrite this, right, using the quotient rule. So to find u prime, we take the bottom, times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. Okay, so the derivative of 5x plus 1, well, the derivative of 5x is just 5. The derivative of 1 is 0, so that'll just be 5. Okay, now here's a derivative we haven't dealt with yet, the square root of x. So actually, up here where I have some extra space, let me just go ahead and talk about the derivative of the square root of x. So that's the same thing as the derivative of x to the 1/2 power, right? That's how we write roots using exponents. And so now we can just use the power rule. So this would be, we bring the 1/2 out in front and we subtract 1. Well, 1/2 minus 1 is negative 1/2. Okay, so we can leave it like that, or we could rewrite it as 1 over 2x to the 1/2, and x to the 1/2 power, as we saw earlier, is the square root of x. So the derivative of the square root of x is 1 over 2 times the square root of x. So this derivative down here would be the constant 2 times the derivative of the square root of x, which is 1 over 2 square root of x. All over, and I put the parentheses in the wrong spot right here, so let me fix that real quick. We're squaring the whole bottom, and so we square the whole bottom, and we get 4x. And so now we can do some simplification. So this would be u prime equals 10 square root of x minus, and we can multiply this out if we want, so the 2's cancel. And so this would be 5x over root x plus 1 over root x over 4x. And I think my math lab will accept the answer as currently written. But one of the things we would normally do is, this is a complex fraction, which we ran into when we were doing limits. And so we probably want to get rid of that complex fraction. And so the way we do that is to multiply by the square root of x over the square root of x. So this would become 10 root x times root x minus 5x over root x times root x plus 1 over root x times root x all over 4x root x. So u prime is 10x minus 5x plus 1 over 4x root x, which is y prime is 5x plus 1 over 4x root x. Okay, and so that's the idea. So what I'd like you all to do is take a moment, pause the video, and try using the quotient rule to do these three derivatives. Or if you'd like for the, use the quotient rule for these three. Okay, so now that you've had a chance to try these, let's just run through these together. So the first one, so z prime. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom. So notice all I'm doing in this first step, which is what we did on the last page, is writing out the rule. So before I even try to do anything, I just write out the rule. I just substitute into the formula. And now we can simplify. We can do these derivatives. So the derivative of 4 minus 3x, the derivative of 4 is 0. The derivative of negative 3x is negative 3. Derivative of 3x squared. The derivative of 3x squared is 6x, and the derivative of x is 1. Okay, and now multiply out the top. So this would be negative 9x squared minus 3x minus negative 18x squared plus 21x plus 4 all over 3x squared plus x squared, and now combine like terms by subtracting. So negative 9x squared minus negative 18x squared becomes positive 9x squared. Negative 3x minus 21x becomes negative 24x, and minus 4 becomes minus 4. And there we go. So that's the final answer. Okay, and so these last other two are going to be fairly similar to that. So to find f prime of t, the first derivative, we just use the quotient rule. So the bottom times the derivative of the top. Notice this notation I'm using in general is not, for what we're doing right now, is not gigantically important. But as we move further into this class and in future calculus classes and future math classes, it is important to be using proper notation. So since the variable here is t, that's why I'm writing d over dt instead of x like I did in the previous problem, because there the variable was x. So then minus the top times the derivative of the bottom all over the bottom squared. Okay, so t squared plus t minus 2 times 2t minus t squared minus 1 times 2t plus 1 all over t squared plus t minus 2 squared. So distribute. So f prime of t equals 2t cubed plus 2t squared minus 4t. So I wrote 42. Meant to write 4t minus 2t cubed plus t squared minus 2t minus 1. So t squared plus t minus 2 squared. And then combine like terms by subtracting those two polynomials on top. So 2t squared minus 2t squared is 0. 2t squared plus 2t squared, minus t squared is t squared. Negative 4t minus negative 2t is negative 2t. And minus 1 becomes plus 1. All over t squared plus t minus 2 squared. And now, actually, as I notice this, I can actually simplify this, I believe, a little bit by using some factoring. So the top is t, two numbers that multiply to get 1 and add to get negative 2 are t minus 1 squared. And on the bottom, I've got, I need two numbers that multiply to get negative 2 and add to get positive 1. So that would be t plus 2 times t minus 1. And then that's squared. And so now you can notice that I can actually cancel those out. So we just end up with 1 over t plus 2 squared. And this is actually an example of where I could have saved myself some time right off the bat. This answer is perfectly fine. It all works out fine. But if you were to factor this before you even started, this f of t can factor as t plus 1 times t minus 1 over t plus 2 times t minus 1. Those cancel out, and if I did the quotient rule with this, I'd get exactly the same answer. Okay, so I could do f prime of t is t plus 2 times the derivative of t plus 1 minus t plus 1 times the derivative of t plus 2 all over t plus 2 squared. And then we just need to simplify. So this would be f prime of t equals t plus 2 times 1 minus t plus 1 times 1 over t plus 2 squared. So f prime of t equals t plus 2 minus t minus 1 all over t plus 2 squared, and then that gives you exactly the same answer as the one we did before. And the work's a little less cumbersome because you're not dealing with as big a polynomial. So that's always something you want to watch out for. So can I simplify the original problem before I try and take the derivative? And we'll talk more about that kind of simplification idea on the next page here in a moment. But before we do that, let's go and do this last one. So w, in this case, this is the bottom, right, because it's raised to the negative first power, which means this is the same as x plus 5 over 2x minus 7. Okay, so we can use the quotient rule here. So this is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So this would be 2x minus 7 times the derivative of x plus 5, which is just 1. Derivative of x is 1. Derivative of 5 is 0. Minus x plus 5 times the derivative of 2x minus 7, which is just 2. Over 2x minus 7 squared. So this would be 2x minus 7 minus 2x plus 10 all over 2x minus 7 squared. So that's 2x minus 2x cancels. Negative 7 minus 10 is negative 17. So this is negative 17 over 2x minus 7 squared. Okay, so that's the idea of how the product and quotient rules work. So now let's talk about a few other things that go along with this before we're done with this section. So the first big thing is the idea of taking derivatives of all orders. So finding derivatives of all orders of a function simply means continue to take the derivative until you get a derivative that remains the same over and over and over again. Okay? And this is most useful when you have something written as a polynomial. So for this first one here, I'm going to multiply this out to get a polynomial. So if I do that, it'll be negative 4x to the fourth plus 8x cubed minus 3x squared plus 6x. Okay? So then if I find the derivative of that, I can use my polynomial room. So y prime is just going to be negative 16 x to the third plus 24 x to the second minus 6 x to the first plus 6. And what you should notice is when I did that first derivative, is all the exponents stepped down by 1. So eventually I'm going to run out of exponents here, and I'll stop. So then we could do the second derivative by applying the same rules again. So negative 16 times 3 is negative 48 x squared. 24 times 2 is 48x minus 6, and then the derivative of 6 is just 0. So that one drops off. So then y triple prime would be negative 92x plus 48. And then the 6 drops off because its derivative is 0. And then the fourth derivative would be negative 92. And now we get to use that notation that we saw at the beginning of class for a fourth derivative. And then the fifth derivative, the derivative of a constant, is 0. And now we'd stop, right? Because if I did that derivative again, I'd get 0 again because 0 is a constant. And so we just keep repeating over and over and over again. So this original function has 5 derivatives that I could find. Okay, so why don't you guys pause the video and try doing that same thing with this simple one here. This should say something like y equals x to the fifth over 120. Okay. So now that you've had a chance to try that, let's do them together. So y prime would be 1 over 120 times 5x to the fourth. So that's 1 over 24 x to the fourth. And then y double prime would be 1 over 24 times 4 x to the third, which is 1 over 6 x to the third. And then y triple prime would be 1/6 times 3x squared. So that'd be 1/2 x squared. Y to the fourth derivative of y would be 1/2 times 2x, which is just x. Y, the fifth derivative of x is 1, and the sixth derivative of 1 is 0. And so there you go. So that's the idea of finding derivatives of all orders. Now, one of the other things we want to keep in mind as we're doing these is an idea I kind of mentioned earlier on, which is you probably don't want to work harder than you need to. So you want to look for opportunities where you could simplify a problem and make it easier to do the derivative. For example, in this problem here, I could just go ahead and do the quotient rule right away, but there might be some ways to simplify this if I multiply out the bottom. So this would be the same as q squared plus 3 all over, and I left a long line because I need to multiply these out. So q minus 1 squared is cubed is q cubed minus 3q squared plus 3q minus 3, and then q plus 1 cubed is q cubed, minus 1 at the end here, minus 1, q cubed plus 3q squared plus 3q plus 1. And so now you can see that'll simplify a little bit. So negative 3q squared cancels with positive 3q squared, and negative 1 cancels with positive 1. So this is q squared plus 3 over q cubed 2q cubed plus 6q when we simplify. And now we can simplify it even further because I can factor out a 2q on the bottom. So this is q squared plus 3 over 2q times q squared plus 3, and now the q squareds plus 3 is canceled, and this is 1 over 2q, and I can do that derivative pretty easily because I simply, I multiply, not equals, so p prime, now I can do this derivative. So I multiply by the opposite of the exponent, so that's negative 1 times 1/2, or 1 over 2, and then I add 1 to the exponent, 2 squared. So this would be negative 1 over 2q squared. Is the derivative of that fairly complicated looking thing. And so that's the idea. Try to simplify things if possible. So the same thing goes for this second one here. One good idea when you're doing most of these is go ahead and multiply out any polynomials you can to get one big polynomial instead of the product of two smaller polynomials, because that way you won't have to use the quotient rule. So in this case, you would be x to the fourth, and then what we get, let's just write all the terms out. So x to the fourth minus x cubed plus x squared plus x cubed minus x squared plus x. Okay, all over x to the fourth. So now negative x cubed, positive x cubed cancel, x squared and negative x squared cancel. So this is x to the fourth plus x over x to the fourth. Now one additional thing we can do here is we can divide this to make this simpler. So this would be x to the fourth over x to the fourth plus x over x to the fourth, which is 1 plus 1 over x to the third. And so that is a much easier polynomial to do the derivative of. Right, so u prime is just going to be the derivative of 1 is 0. The derivative of x to the third is multiplied by the negative of the exponent times 1, the exponent added 1, so x to the fourth. So this would be negative 3 over x to the fourth. Okay, and the same thing then is true for this last one, right? I can use the division idea I used up here, so this would be t squared over t squared plus 5t over t squared minus 1 over t squared. So that's 1 plus 5, not equals 1. When I simplify that, that's 1 plus 5 over t minus 1 over t squared. And then I can do that derivative. So s prime would be, well, the derivative of 1 is 0, so that just goes away. The derivative of 5 over t is negative 1 times 5 over t squared. And the derivative of t, 1 over t squared is negative 2 times 1 over t cubed. So s prime would be negative 5 over t squared plus 2 over t cubed. Okay, and so that's the idea of how to use these rules we've talked about so far. Now the last thing we want to look at before we are done with this video, sorry, this one's been pretty long, but there were a lot of things to look at in this section, is just an example of some stuff we can do with these problems based on what we've given. So find the equations for the horizontal tangent lines to the curve, x cubed minus 3x minus 2. Also find equations for the lines that are perpendicular to these tangent lines at the point of tangency. What is the smallest slope on the curve? And at what point on the curve does the curve have this slope? Find an equation for the line that is perpendicular to the curve's tangent line at this point. Okay, so the first thing is we're talking about slopes of tangent lines, right? And so what you want to start out by doing is find the derivative, right? Because the slope of the tangent line is equal to the derivative, the first derivative. So y prime here would be 3x squared minus 3. Okay, so the first thing it's asking is to find out when it's horizontal. Well, horizontal lines have a slope of 0. So what we want to do is we want to figure out where does this have a slope of 0. Okay, at what points does this have a slope of 0? So set this equal to 0 and solve. So this would be 3 equals 3x squared. So this would be 1 equals x squared. So that would be plus or minus 1 equals x. Okay. Okay, so those are the x-coordinates where we have a slope of 0. Now we need to know what are the y-coordinates that go with those. So to find the y-coordinates of those, what you want to do is you want to plug them into the original function. So I need to do y of 1 and y of negative 1. So that would be 1 cubed minus 3 times 1 minus 2. And this would be negative 1 cubed minus 3 times negative 1 minus 2. And so then that's 1 minus 3 is negative 2. Negative 2 minus 2 is negative 4. This one would be negative 1 plus 3 is 2. 2 minus 2 is 0. Okay? And now if you want, you can use the point slope form to find the lines that happen at those points. So that would be y minus the y coordinate for 1, so that's negative 4, equals 0 times x minus 1. So that's y plus 4 equals 0. So that's y equals negative 4. So there's one equation of a horizontal line. Okay. And then the other one, we do the same thing, but what you're going to find is similar to this one where we found negative 4 to be our line. We're also going to get y equals 0. Okay. So those are the horizontal lines. Now, what we know, the other thing they ask for is the equations of the lines perpendicular to these. Well, lines that are perpendicular normally have opposite reciprocal slopes, but 0 does not have an opposite reciprocal. But one of the things you should know is horizontal lines are perpendicular to vertical lines. Well, what are the vertical lines that go through these points? The points 1, negative 4 and negative 1, 0. Well, they're simply the x equals these two numbers. So the lines perpendicular at those points would be x equals 1 and x equals negative 1. And so that answers the first part of that question. The second part of that question is, what is the smallest slope on the curve? Well, we have this equation for our slope of the curve, y prime equals 3x squared minus 3. So the question is, well, when is that smallest? Well, the easiest way to answer that question is by trying to graph it. So if we graph y equals 3x squared minus 3, we get that the smallest slope, the lowest point this goes, is negative 3. Okay, so at the smallest the slope gets is at the point 0, negative 3. So what is the smallest slope? Well, that's negative 3. At what point on the curve does it have this small slope? Well, that's at 0, negative 3. Actually, it's not at 0, negative 3. It's at x equals 0. So what we need to do is do y of 0. So that's 0 cubed minus 3 times 0 minus 2. So y of 0 is negative 2. So that happens at 0, negative 2. And then find the equation of the line that is perpendicular. And then so then it says, at what point does it find an equation of the line that's perpendicular to the current curve's tangent line at this point? So we have a slope. One of the things you hopefully remember from college algebra is that perpendicular lines have opposite reciprocal slopes. So if this slope is negative 3, then the opposite or reciprocal of that would be positive 1/3. And so now we can use point slope form along with this point where this happens to find the equation of that line. So that would be y minus negative 2 equals 1/3 times x minus 0. So that's y plus 2 equals 1/3 x. So that's y equals 1/3 x minus 2. Okay, and so that's the idea. So why don't you guys pause the video for a second, see if you can figure out this last problem, and then we'll work on it together. Okay, so now that you've had a chance to try it, let's go through it together. So find all the points x, y on the graph of g of x equals 1/3 x cubed minus 3/2 x squared plus 1 with tangent lines parallel to the line 8x minus 2y equals 1. Okay. So one of the things hopefully you remember is that parallel lines have the same slope. So there are two things we need to know. We need to know, well, what is the slope of this line that we want to be parallel to? And we need to know what are the slopes of all the points on this graph. So if we start out by finding the slope of this line, so 8x minus 2y equals 1, we just solve for y, right? So this would be negative 2y equals negative 8x plus 1. So y equals 4x minus 1/2. Minus 1/2. Okay, so the slope here is 4. It's that value. So now the second piece of information we need is we need the derivative of this function g of x. So we find g prime of x, which would be 1/3 times 3x squared minus 3/2 times 2x plus 0, because the derivative of 1 is 0. And then we simplify. So this would be x squared minus 3x. And so in order to, now all we have to do is find those points. So what we first have to do is find the x-coordinates. And to find the x-coordinates, we use the derivative. So we set the derivative equal to the slope we want, which is 4. So this would be x squared minus 3x equals 4. And then we solve that equation. So this would be x squared minus 3x minus 4 equals 0. And then we can factor. So that's x minus 4 times x plus 1. And so we get x equals 4 or x equals negative 1. And then you just have to find the ordered pairs in the original function that go with those x coordinates. So that's going to be g of 4 and g of negative 1. So that'll be 1/3 times 4 cubed minus 3 halves times 4 squared plus 1, and 1/3 times negative 1 cubed minus 3 halves times negative 1 squared plus 1. And here's a good place to use a calculator. I won't bring it up on the screen because it's easier if I can see this screen and do it. But I'm going to use a calculator to figure this out. So 1/3 times 64 minus 3 divided by 2 times 16 plus 1 as a fraction is negative 5/3. And we do the same thing for the other one. So 1 divided by 3 times negative 1 minus 3 halves times positive 1 plus 1 is negative 5/6. So the 2 points are 4 comma negative 5/3 and negative 1 comma negative 5/6. Okay, so that's it for this section. Sorry, this was kind of a long video, but like I said, there was a lot of stuff in this section. Make sure you're keeping up with the assignments on my math lab, and if you have any questions, feel free to contact me by email or in the Remind app, and we can talk more about it.